Welcome everybody to Optimization in Oslo. Very nice to see all of you here today, virtually and in the room. Today we have Hintermüller from the Weierstraße-Institut and Humboldt-Universität in Berlin. He's going to talk about PDE-Constrained optimization with learning-informed structures. So we're very happy to have Michael with us today. So the floor is yours.
Well, thank you very much, Thomas, for the kind introduction, also the kind invitation. As we just discussed, I wish to be in Oslo these days. I had planned it firmly, but then there were some other commitments and finally I can do it online only, but I'm looking forward to coming to Norway certainly sometime next year. So this is a talk which is based on 3 papers actually. So one is published in COCV and the other 2 are available on arXiv. And all of them are jointly with the 2 gentlemen whom you see in the bottom line here. Guo Zidong, who has recently picked up from a postdoc position out of my group a professorship in China. And the second one is Kostas Papafistos, who was also postdoc in my group and is now professor in London. Now, what is the topic about? Let's start with modeling, more the classical paradigm. So I would say the classical modeling paradigm could be considered as follows. You have some input parameters, call it scenarios or design of experiments. Then you have a physical experiment and you generate outputs, measurements of states or whatever you can perceive out of this system. Of course, this can also be done for specific physics-based models. And when I say physics-based model, I really mean the first word like it. So it's like an experiment where I generate from input data some output data. So then you observe the system. And a typical model paradigm would, I guess, do the following. You go back to basic principles, fundamental constitutional laws in physics, and come up with a new model based on the data which you observe. And these models would then be called ab initio models, which typically then use for analyzing the experimental data, but also for prediction of other behavior of this underlying system. Of course, there are several challenges. One challenge is to make these models increasingly more accurate on the physics side. And this is certainly a continuous challenge, which we see on our experimental science sites many times up to this day. Secondly, of course, you may also wish to have just the consideration to take the input and output data as the underlying. And then you're would not want to go back to ab initio models, or at least not completely, and try to learn model constituents, components, or entire models just from the data. And for this, it has turned out in recent years that artificial neural networks are very efficient tools to learn physical laws from such data. And this will be more or less the perspective of this presentation now. And of course, it also helps that our increasing computing power allows us to collect more data and compute more and more complex models. For instance, we see some recent trends in quantum machine learning where I can even have access, hopefully in the near future, to quantum computing facilities in order to even crank up the overall size of the instances. Now, sticking to the second item, artificial neural networks, what would be a corresponding paradigm? And this is more or less the slide, which still has the same structure as the one before, but tries to go away from the classical ab initio to more data-driven learning-informed models. And I'll also introduce some notation on the fly. Let's assume we have input scenarios, which are called UI, I from 1 to capital N. So you have capital N many scenarios. You may call them controls, parameter settings, design of experiments, or whatsoever. And then we assume we have a physical process, which is partially at least unknown, could be completely unknown, and it generates output data yi, where yi is generated to u is related to ui, and I again goes from 1 to n. And I would like to use these data collections, ui, yi, in order to learn a model which I call pi sub n. So the physical process is called pi, which takes a u and maps it onto a y. You may call in following control terminology u the control and y the state. And then the learning informed model would do more or less the same, but there's a little n attached. It's a curly n, which should remind us that there is some learning informed component inside, or the pi n is entirely conceived from data only. And this is an interesting object in its own right to study for many reasons, analytically from an approximation theoretic point of view, but also from a numerical solution point of view. But this will not be so much the focus of my talk today. I would rather do what you see in the green box on the right-hand side, which is plugging this kind of constitutive relation between parameters, controls, u and states y as a side constraint into some control problem, as I may call it here. So where you try to find a control u such that the given state y after some output generated by an operator A matches as best as possible some given data G. So this is the meaning of the objective. The second term with the alpha positive would be an average cost of a control. And the control U, of course, can also have certain constraints hidden in C admissible here. So this problem in the green box pretty much motivates the rest of the talk. And of course, it works for optimal control of PDEs, but also or differential equations or other structures, but also for optimal control for inverse type problems where you would be a parameter you're looking for measurements of the state Y, which are transformed through some operator, some measurement space where you can record the G, so to speak. So that formulation that would be good for optimal control of PDEs, but also for inverse problems in a sense. Now, the talk is motivated in its majority by two applications. You see on the left-hand side a kind of snapshot of a phase separation process. You may, for instance, know the Cahn-Hilliard equation or the Allen-Cahn equations. They are trying to model phase separation. Imagine at some time zero, you have a homogeneous mixture of, let's say, a binary alloy or a binary fluid. And then over time, the fluid demixes, like oil and water, for instance, or other kind of substances. And this demixing is described by the Allen-Cahn or Cahn-Hilliard equation, depending on the setting. And then typically you have a diffusion process along with the nonlinearity modeling the phase separation. And you may assume in such a setting, for instance, that the diffusion can be modeled pretty well by ab initio considerations, but the nonlinearity, which is sort of homogeneous for energy density, is a delicacy in its own right and can be learned from data. So in that sense, we end up with a hybrid PDE, which has some data-driven components from machine learning added to some ab initio models, for instance, on the diffusion side. The second application on the right-hand side, which says quantitative MRI, goes back to magnetic resonance imaging, where the desire is from measurement data in frequency space to extract quantitative information like relaxation times or proton densities, which are then uniquely related to specific tissue types. And again, it's a similar process as outlined in the green box, where you have measurement data G, some transformation A into some frequency space, where you record G, and you would like to learn something about the state Y, which in the case of MRI would be magnetizations. And the U would be the parameters like relaxation times and proton density, but I'll get there. Now, before I continue, let me give you a little bit of a guideline to the remainder of the talk. I gave you some motivation, I hope at least. I'll say a few words about deep learning in its current state, put under quotation mark, because as we all know, there's a lot going on these days. And when you report on one day, it could be partially outdated the next day. So in that sense, bear with me if I haven't on the record the latest developments or your most recent paper on this. I'm certainly happy to add this, but this is just a glimpse at it as far as I can do it in this presentation. Then I'll return to my initial setting, optimization, constraint, learning, informed models, talk about some general results, then flash up a specific PDE which has smooth components and a PDE which has non-smooth components. I'll tell you more about the distinction later on. Time permitting, I'll say a few words on the application of this quantitative MRI and conclude at the end of the presentation. Now, what could be, just as a starter, a glimpse of the mathematics of deep learning and its current state as it's relevant for this presentation. Just to fix a bit notation understanding, I think many of us have seen this kind of schematic or a similar one of an artificial neural network of feed-forward type. We have an input layer highlighted here in yellow, and then you have three hidden layers, all of the same size in my little example, but that may not be the case. And you have an output layer, which is the red layer here. U would be the input data, which comes in from the left, and Y would be the output data, which is relevant for the right. And in between, you have a transition from one layer to the other in the following fashion. You have some current vector HL, say, and the HL is being affinely transformed by these quantities WL, a matrix, plus BL, a shift vector. And after this affine transformation, you're more or less cutting off or activating neurons or deactivate neurons by this function sigma here. And this generates the output vector on the next level, HL plus 1. And then you repeat this process until you go from the input layer all the way down to the output layer. I've given you down here a one hidden layer case where you start with an input, already using my terminology U here as an input parameter. You affinely transform by W0, P0, you activate by in a component-wise fashion by the function sigma, and then you transform once again, and then you hit the output Y. And now the task in learning here would be from given data pairs y and u, or u and y rather, you would like to learn the unknown parameters hidden in WL and PL. And this can be done by solving this generic optimization problem, which I have put down there, where the first term is a kind of data fidelity or data discrepancy term, if you wish, where you have a map n from uj to yj, and then you try to somehow define a mismatch there. The second term is a regularization term in order to implement some a priori knowledge. For instance, you may wonder whether W should be sparse or not, and then you can sort of model this by specific choices of R. And you may have additional constraints here hidden in F admissible on W and P for further properties. But this problem, in particular, if the instances are large, which means you have many data, could be very complicated to solve. And as we speak, many of our colleagues in optimization try to develop and design innovative methods, for instance, of stochastic nature in order to cope with the size of the problem, but also the nonlinearities and other aspects involved. So while this is a sort of important task and art in its own right, this will not be the focus of my presentation. Let's assume for the rest of my presentation, given the data uj, yj, we already have computed this model n, which means we have found the parameters in wi and pi, the corresponding matrices and shift vectors, so that we can conclude on this process has been achieved, while of course it's also interesting to further intertwine this process later on with what is going to follow in this presentation. But again, we assume we have a model curly n at hand because somebody has solved our problem. Now, what do we know in terms of approximations? I don't cite, of course, exhaustively, but just some basic aspects like universal approximation. We are considering mapping F on a bounded domain omega in finite dimensions in Rm, say, with output space Rn, and then the fundamental approximation theorem by Cybenko, which is nicely summarized in this Acta Numerica article by Pincus down there, says the following. If you look at the network as we have just done a minute ago, which would be a multi-layer feed-forward network with a continuous activation function, so assuming that the sigma is a continuous function, then it can uniformly approximate any continuous function to any degree of accuracy if and only if the activation function sigma is not a polynomial. So this is, of course, a density result saying you can get as close as you wish to a function f unless the sigma is a polynomial. This is also, of course, good to know because this tells us something about the qualitative nature of using neural network type approximations for functions. And if you increase regularity, then you can, of course, crank this up not only to function values, from function values to derivative values as high as you wish, depending on, of course, the underlying regularity. And the second theorem does precisely this. It says you can also densely approximate the derivatives if there's enough regularity, of course, involved. This again also involves the regularity of the activation functions. Plus, again, the activation function is not allowed to be a polynomial. So this is one type of approximation, which is qualitative only. It's not quantitative in the sense it will give you a size of network or an approximation rate, but it at least tells us there is a density with these kind of approximations. And I focused on activation functions. And for the first part of my presentation, I'll stick to smooth activation functions. I give you two famous example groups here. One is the sigmoidal type functions like the transig or the logsig or the arctangent, for instance. But there are also probabilistic functions like the softmax, as I have highlighted down there. It's also observed in many applications, in particular when sparsity or other aspects are relevant, that the rectified linear unit, which is this max type function, has very good properties. But of course, transiting from sigmoidal or probability to the real function means going from the smooth to the non-smooth world. And I'll tell a little bit about the complications in analysis, but also numerics when you do this kind of transition. So again, for the first part of my presentation, everything is smooth. You may assume that sigma is a C infinity function for the sake of simplicity. Now I'll highlight it whenever I go away from this assumption to a non-smooth activation function, tell you about the consequences of such choices. Now, what else is available? Now, for instance, again, we have 4 cases here. When F, the underlying, is defined from a bounded set omega in finite dimensions to Rn, then the universal approximation theorem, as just discussed, are available. And I think this case is pretty much well understood. And specific examples or applications would, for instance, be generalized regression examples. It gets more and more important or irrelevant or tricky the more infinite dimensionality you would incorporate. Cases 2 and 3 have infinite dimensional domain or range spaces. With the first example, again, going from some subset of a Banach space B1, which might be infinite dimensional, into finite dimensions, is work which is under development, but somewhat reasonably well understood. Mostly we see convolutional neural networks in this kind of setting, and a specific application falling into this class would be image classification. What is also more important these days is rather using finite elements as a discretization for solving PDEs. We produce neural network type parameterization of PDE solutions and then try to find the corresponding parameters in these W and P vectors and matrices as discussed before. In such a setting, you start from a finite dimensional domain omega in Rm, and you map your solution into some infinite dimensional space P2, which is again here assumed to be a Banach space. And again, application will be solving PDEs as an example, but also ODEs can be, of course, discretized like that. And the final case, which could be most important for us at some point, is the most difficult one, where you have, for instance, in your mind, a solution map or partial differential operator, for instance, partial differential equation, for instance, learn from data. In this setting, you start from an infinite dimensional space and end up in an infinite dimensional space. And the context would be operator learning as just explained. And this is, of course, still work pretty much under development. The major obstacles, obviously, for 2 to 4 compared to 1 are compactness conditions, which are, of course, in finite dimensions, easier to achieve than in infinite dimensions. And this is pretty much the dividing range, I would say, between these classes. Then, just to fix a bit terminology here in order to not confuse people, you may have heard about physics-informed learning, and I will talk about learning-informed physics. So they are not the same. It's not just a permutation with the same meaning, but there's a difference. Physics-informed learning is a situation where you may assume that you have some PDE model, for instance, at hand, modeling a physical process, and then you use an artificial neural network in order to discretize the partial differential equation. In a sense, there's function which should solve the PDE by this mapping N, and then you try to find these parameters W and B by minimizing an objective function, which typically involves the PDE residuals as loss functions in the training phase. Whereas learning-informed physics is different. Here you have physical models being predicted by data, and you may either predict entire models, like solution maps for PDEs or ODEs, but you may also just, as in one of the examples I'll highlight in a second, just learn specific constituents and then benefit from other solution processes which you may have at hand already. In such a situation, the loss function is not necessarily a PDE, it's different. And we are typically in the setting 4, as I just explained on the previous slide. And for the sake of completeness, I'm happy to share my slides. I give you some relation to work which touches upon these different cases. Now, I'll go back to my initial second slide about this green box now and talk a bit about optimization constraint for learning informed models. And for this sake, I'll go again back to this problem which you've seen in the green box, which is minimizing a specific objective. It could be slightly different objectives. That's not the major point, but these tracking type objectives are very often seen in practical applications, but again, you could use other objectives as well. The little e here maps models a partial differential or ordinary differential equation connecting a control U to a state Y, and U, the control, may also have some constraints modeled in C admissible. The operator A is supposed to be bounded and linear, alpha is supposed to be positive, and this would be a typical control type problem. As explained earlier, or also would fit the context of inverse problems where we use a parameter to be identified from measurement of output data A, Y, or G. Now, if everything is well posed, you can use the implicit function theorem and state that given a U, we can resolve the PDE at least locally uniquely, maybe globally uniquely, so that Y can be written as a mapping pi of U, which would be the implicit map or the solution map for the OiO or the PDE. And of course, our underlying assumption is that we don't have pi of U available, but in one way or another, we end up with the pi sub n, which then includes learning-informed components, again, in one way or another, either via some constituents, like this Alan Kahn situation as discussed earlier, or by learning the entire solution map as I'll do, for instance, for the quantitative QMRI situation, the MRI situation. What could be several immediate questions? Of course, there are many. I'll just highlight two here. Well, first of all, of course, you may wonder what are the conditions for well-postness of the learned physical model, and how does it work in view of universal approximation theory when it comes to the operators pi versus pi. And of course, other aspects could be approximation properties of optimizers, qualitatively or quantitatively, of the learning model versus those related to the original physics-based models. And of course, this goes on to higher order information, first or second order information as well. Now, a first result, which I'll highlight here, is about existence of solutions. For the sake of simplification, let me call Q this superposition of A after pi. If I just go back one slide, oops, wrong direction. Then this would be the situation where in this objective, the A of pi n or the A of pi gives rise to this Q or Qn, depending on how we would like to denote it, which allows us to reduce the problem to a problem in the control variable U only. As you can see, that the Y disappeared by this implicit function theorem aspect. And this is what this Q in essence does for us on this next slide. So it helps us to reduce this problem. And then if this Q is weakly sequentially closed, meaning if you have a weakly convergent subsequence UN to U in the
lost him. Second.
Here. So I said, okay, I'm just recapping a little bit because of the interruption. So the Q here is supposed to be a superposition of A after pi. Remember, pi is this implicit solution map as a solution operator for the underlying equation, say PDE. And the pi sub n is the one for the one which is learned from data. So no network-based one. And then the proposition says you have existence of a solution if Q is weakly sequentially closed. And you can weaken this assumption to strongly weakly sequentially closed if some compactness with respect to the control constraints or the control space is going on. This second property very often be, for instance, gained in inverse problems by specific settings, but sometimes it's also helped the weakly sequentially closedness aspect by regularity properties of underlying PDEs, where the state gains regularity as opposed to the measurement space H, and then you can benefit from compact embeddings of those spaces, for instance. But at least this gives us an idea under which conditions we have existence of a solution for the original problem, but also the learning form problem. Now we move a bit further and have to learn about approximation properties. Now for this, the Q sub n is the superposition of A after pi curling n sub n, which should indicate that we have a sequence of networks. Typically, you may assume as n increases, the little n increases, also the size of the network increases somehow. And then we try to study convergence of the solutions of the learning-informed optimal control problem versus the original one. For this purpose, let's assume that Q and Qn are weakly sequentially closed operators, satisfying this approximation property in terms of a sequence epsilon n going from above to 0, where the relevant instances to plug in are, of course, feasible controls and C admissible. If that takes place, then if you have a sequence of minimizers UN of the learning informed problem, then it converges strongly up to a subsequence, as is indicated down there, to a solution of the original optimization problem. And the same is true for this operators Qn of UN, which would then strongly converge to Q of U bar. So again, we have this kind of approximation property as well. So in that sense, we are good to go with existence of solutions. And we know that as the instances increase and get better in terms of approximation of the original operators, we'll have convergence. Of course, there are two things to say. Number one, the assumptions of having such an epsilon n needs to be still discussed. This, of course, would go back to this kind of idea based in universal approximation theoretical settings. And the second aspect is, can we say something about rates here? Now, let me start with the second aspect, and I'll just go to the next slide for this. Let L sub 0 be the Lipschitz constant for the operator Q, and L sub 1 the one for the Q prime operator. And the eta, the Q prime is the Fischer derivative of Q. Everything is assumed to be smooth. Again, Remember, I said in the first part of the presentation, activation functions are smooth. The eta n is simply the error in q prime minus q prime n, the corresponding operator norm. And then on the smallest assumption on the Lipschitz constants, you can show that the approximation quality of un towards u bar, un being the solution of the network problem with qn, and u bar being the original solution, is of this type, capital O, which hides specific constants, but nothing critical. You see how the L0 appears next to the epsilon n, plus this residual q u bar minus g from the objective times the derivative error here. So in that sense, it's first order in both errors, if you wish, unless you have a zero residual problem where the eta n error plays no role then. The second theorem touches a specific setting, which is the one where the control constraints are redundant. So you can see that in this case, only the reduced objective J prime is equal to 0. You don't have to solve a variation inequality as it would be the case for a setting where control constraints may be active. And then I haven't given you the condition for the first theorem, but the second condition, which is highlighted down there, is a bit weaker in terms of L1. There's no L0 appearing, relates L1, the residual Q u bar minus G, to the control cost alpha, which admittedly can be small. So there is a restriction on this condition. But for instance, the perfect matching case, there's no restriction at all. And in this setting, you get this estimate down there, which again is first order in epsilon n and tells us how the residual Q u bar minus G enters in the upper bound. This is a bit related to source type conditions, as you may know it from inverse problems, but it gives us now an idea about some rates here. Now, this would conclude the more general setting. I would now go into specific case study to make it more plastic, so to speak, in terms of applications. Now, let's stick to a specific, admittedly simple, but I think you get the spirit, PDE here. So you see, I'm focusing on a control problem where the operator A and the objective is just the identity. The space H is L2, the control space is L2 as well, over some bounded domain omega. Otherwise, the objective is as before. The PDE, the little e, has a specific form now. It's of a semilinear elliptic type, where we have a hybrid situation where the, let's say, diffusive part, the negative Laplacian, is coming from ab initio modeling, but the nonlinearity F, which may depend on the location omega as well, and of course on the state Y, is inferred from data later on, and the control sits on the right-hand side, but of course other settings would be conceivable, like boundary control and so on and so forth. And to give you an idea about control constraints, we simply have here a box like bilateral bounds, u lower bar from below and u upper bar from above. Now, again, as I said in my motivation part to this presentation, the F may not be known completely, but just come from data-driven aspects. So in that sense, this is my partially unknown differential operator, where the F needs to be inferred from data. So this is our goal there. So which means the pi is replaced by a pi n, or the F rather, I should say, is replaced by a curly n, where the curly n is a neural network map. And this can be learned, for instance, from residuals from the PDE or from direct measurement data, depending on the processes which you have at hand. And so in that sense, you have a hybrid PD situation where, again, there's a fixed component and a data-driven component. And of course, the control to state map is now this pi sub n, which would be the map solving this equation as it's highlighted here with this red constituent here, the neural network function. Let's say a few words about the analysis of this problem. Let's assume the underlying F is, as you would expect it for those who know about semilinear elliptic PDEs, should be Caratini-Adori function. It should satisfy certain growth rate conditions as highlighted here with some power P. The P is related to this embedding of H1 into LP, as you see down there. We assume that the primitive function capital F of the little f is coercive, as written down there, and bounded from, the primitive is also bounded from below. Under such a setting, we are able to understand this specific semilinear elliptic PDE as a first order optimality condition or a Lagrange equation for a variational problem, which are highlighted up there, which is the inf of a capital G of Y, which tells us that we have the diffusive part of the first component, the homogeneous energy density, the capital F, the second component, and the control acting here on the right-hand side on the right in the last component. And we can say that if the control is sufficiently regular in terms of Lebesgue regularity, as highlighted here regarding the P, remember H1 embedded into LP. Then, of course, from Sobolev embedding, you can trace the P's, which do the job for you. You can then say that the optimization problem or the variational problem admits a solution, and the first order conditions are really the PDEs. And that says the PDE admits a solution, all is fine. So this is the proposition. Now the theorem says something about the regularity and the boundedness of the state Y, which will be relevant in a second. I'll tell you why. Now let's assume C admissible is in L infinity, so which means our U lower bar, U upper bar would be L infinity bounds or simply just constants. Then it turns out that there is a constant K, such that for solutions where after simulating the PDE, it holds that not only the H1 norm is bounded by such K, but also the C of omega bar norm is bounded by that K for all feasible U. And again, U is bounded in the C admissible is bounded in L infinity. This is where I get this uniform bound K also acting on the Y here. I'll tell in a second why this is important, but before I go there, let's return to this approximation question. Remember, I had this operator Q and Qn in the general results saying if those are less, the difference is less than some zero sequence epsilon n, all works fine. Now this is here more or less related to the functions f and n. And you can, of course, say that using universal approximation theoretical results, the density of these neural network approximations under the given conditions, then you can take any epsilon positive, and there will exist a neural network function n such that it approximates the f well over this bounded range of y and L infinity less or equal some k. And of course, also the learning informed model then admits a weak solution satisfying this upper bound. And for this, of course, we only need this bound y less than k. Remember, universal approximation results say that our mappings should be over some bounded sets. On the first component of the little f, you have x. X is out of omega, and omega is supposed to be a bounded domain. And the y is the functional variable, but is also bounded by k. Hence, whatever you plug into the f, the first and second component will always be in a bounded set. And this is what you then use for implying the universal approximation result to approximation quality. Now, what about sensitivity? Let's assume you have a U naught, which is a reference control, which you perturb in direction h by some TNH, where the TN is a zero sequence, a null sequence. And let's call the UN the corresponding perturbed control and the YN the corresponding neural network-based state, where YN converges to some Y0. You can also look at the rate of this convergence. Yn minus y naught would be less or equal CTN. As expected, is a classical Lipschitz property with some constant. And of course, now you can form the quotients Yn minus y0 over Tn. They will be bounded, hence there exist weakly convergent subsequences and each weak cluster point, which I call P here again. As I noticed the overloading with the P, which was up front, but now P is really a function satisfying this PDE down there, which is a reminiscence of the adjoint equation somehow. And again, the P has this bound as highlighted in the equation down there, which is of course is not a surprise. With boundedness of P in terms of H1 intersected the C infinity over omega bar less equal to constant times the update direction or the perturbation direction H here. Now, I'm giving you just a little example here for the Allen-Carney equation. A double well potential and its corresponding derivative look like what you see here in the blue curve. And given some data, you can see some approximation in red, which is the neural network-based approximation. And what I wish to highlight here is the following. On the right-hand side, you see a very good matching in the range between -2 and 2, of course, depending on the data which was available for learning this mapping. And I do not care so much about the other parts here, because the physical relevant range for this application really is just -1 to 1. And in this setting, what is important is, of course, that if you go to the next page, you see a good matching in the physically relevant range between -1 and 2, or maybe the neighboring. And left and right of this region, you need to see certain growth in terms of the speed of a penalization, but otherwise there is not much else needed, and you still capture the physics very well. Now, what can we say about the solution maps for the PDs? I was talking about F versus N, and the approximation quality, which is granted by universal approximation theory. And this approximation quality up to a constant is also inherited by the first blue line, by the solution maps for the semi-linear elliptic PDEs, which are for the original PDE, the pi, and for the neural network one, remember where this little f is replaced by the curly n, is the pi sub n, and again you have this approximation of order epsilon. The constant has to be, of course, comes from the corresponding PDE operator setting. And the same, of course, is true under regularity assumptions on f, and the derivative of f and the neural network function n for the adjoint states pi 0 minus pi epsilon. Now you have errors which are on the one hand side epsilon, which comes from the 0 order approximation quality, and epsilon 1, which comes from the first order approximation quality of f versus n. Now we have everything at hand. We know that we have existence of solutions, we have convergence of solutions, we have approximation quality of solutions, and also the adjoints, and we can set up now the Karash-Kontaka system for the neural network-based optimization problem, which I'm doing here in the upper part of the presentation. You can see here that the state equation, the first line, the adjoint equation, the second line. You can see optimality with respect to U in the third line, and complementarity conditions were written using a max and min terminology with some fixed positive C in the last line. Now this system, after some reformulation, not immediately, but after some reformulation, which in a sense replaces the lambda from using the third equation here in the fourth equation with an appropriate choice of C, namely if C equals alpha, you can prove that the resulting system is semi-smooth, and so you can apply semi-smooth Newton method for solving that system. Every semi-smooth Newton step, which linearizes in a generalized sense the remaining system, can be of course interpreted as the solution of an associated quadratic minimization problem, which I've written down there. It may offer you also specific choices for HK in case you wish to diverge from the classical linearization with some quasi-Newton type approximation or similar. Given some iterate UK, that you compute then solving this problem, the update direction delta U, so the semi-smooth Newton method would give you, and then you have to decide by some line search process, for instance, using this penalty type merit function up there, non-smooth merit function. You decide on the step length mu k, and this is what allows you to go from UK to UK plus 1, and that's what we in essence do in our numerical process. So there's nothing fancy there. So it's like a classical SQP. What you see here is again an example using the stationary Elm-Kahn equation, where on the left-hand side you see the control and state pair. So the state is in the upper part, which is the so-called order parameter, which ideally should be 0 or 1 or -1 or 1, depending on how you scale it. You see here in this range going from red to yellow, the so-called interfacial region, which is related to this fact that we talk about the phase field modeling aspect here. And this is where you see diffusive interface. And down there in the second row, again, first column, you see the associated control UN. In the middle column, you see the corresponding quantities for a true physical law, which are the corresponding states and controls. Visibly, there's not much difference. And on the right column tells you quantitatively the difference between the two solutions. You can see that the neural network approximation works reasonably well, and we used here around 300 to 353 parameters in WMP to be identified from data. And yeah, I think this would be merit function numbers. All works fine as expected. Now let me switch from smooth to non-smooth PDEs. And they may come in two fashions. Number one is either your little f, which is the underlying constitutive law, is non-smooth per definition, or you have a smooth f, but for your neural network approximation, you choose a non-smooth one, for instance, using some off-the-shelf learning process, which uses the ReLU. In such cases, the f, or you may replace the f mentally by the curly n. I will not switch between these two. I'll just stick to the f here. Will be not differentiable. So that's what non-smooth means. The max obviously has a kink at 0. And whenever you hit the kink, you cannot just compute the classical derivative. And this causes some problems there. So and this is what I would like to highlight now in the next talk. So again, the f may be non-smooth, the n may be non-smooth, the f may be smooth, but then the n could be non-smooth. In any case, we talk about the non-smooth constituent in this specific location of the PDE there. Well, then it turns out you cannot just simply go to KKT theory, a la Curtius, and write down first order conditions, but you have to acknowledge the fact that this N is non-smooth, and you end up with different types of stationarity concepts, as those colleagues who work, for instance, on mathematical problems with equilibrium constraints or other non-smooth structures would be familiar with. And of course, this has an analytical component, but also a numerical component, because ultimately you need to solve the corresponding problems by genuinely non-smooth solvers. Now, what about such stationarity systems? Now, if this solution map pi of u equals y is directionally differentiable, this is what this pi prime at u bar direction h means in the second spot here in the first equation, then you can characterize the solution u bar as being Polygon stationary if it satisfies this variational inequality over the tangent cone with respect to the set of admissible controls admissible at the solution u bar, which I've highlighted down here. Again, it's the usual tangent cone, as you can see, the pronounced Shapiro. Again, this is a primal concept. You don't see any dual quantities, and you need to have this directional differentiability of pi prime at hand, which, for instance, can be shown analytically if you go for sigmas which are Relo type functions. You end up with a specific structure and can prove that there is this kind of directional differentiability available. If you would like to remove or go from primal to primal dual stationarity concepts, there are two at hand. Number one is C stationarity, which has dual quantities P bar, but also a chi quantity there. And you can see the state equation in the first line. You can see the adjoint equation in the second line. You see this multiplies chi and the adjoint state P, which have to satisfy that chi is in this Clark. That's what the sub C means down there. Subdifferential of the N at the solution y bar. And the last one is just usual variational inequality for optimality of the control. Now, the difference between this C stationarity and strong stationarity is that in the case of strong, the product chi times P pointers almost everywhere over X in omega has to satisfy a kind of sign condition, which is encoded here by using the N prime plus the right limit and the N prime minus the left limit, which can be computed because after all, the N is in this little example a scalar valued and all is fine. So we talk about sensitivity along a scalar valued function, which of course as input has X in omega, could be subset of Rn, and Y, which is again scalar valued in my example here. But that's the difference between the two. Now, how are these concepts related? Well, let's first define a few things. Number one, omega sub f is a subset of omega. Let me check for time.
Yes, time.
Okay, good. So it's a subset of omega where f is not differentiable. Remember, for the Marx function, the kink is at 0, but we need to know where the kink occurs depending on the choice y bar, on the specific function y bar. Then omega A B is the union of the active sets with respect to the lower bound. U so should be U under bar, which is here A, and the U upper bar, which is here B, and the U upper bar here is the solution. So there's a bit of a conflicting notation, but I think you get the idea. And I'll also refer to constraint qualification, which is the following one: all those sets are assumed to be measurable, plus the intersection of the non-differentiabilities of F and the activities of the control with respect to the upper and lower bound happens that with the back measure 0. Then we can show the following results. If you're locally optimal with y bar, u bar, you have P stationarity under the assumption that F has properties. If you have a piecewise C1 and globally continuous function F, which for instance is relevant in the Relo case, because remember Relo comes along by F finally transforming and then taking the max, which gives rise to a piecewise C1 function ultimately. If you have such a structure and local optimality, you end up with C stationarity. If you have C stationarity and the constraint qualification holding, then you can prove that also you get strong stationary points. Strong stationarity implies P stationarity, and the other way around requires a constraint qualification, which is somewhat strong because it requires that the tangent cone of the visible control set CAD at the solution U bar is dense in L2, which means in essence that the constraints are redundant on the control. But that's the collection of results which we have at hand. Now, of course, you may wonder, what can I really achieve now computationally? And we have at hand a solver which can guarantee some version of C stationarity, but in a good setting can also come out with a p-stationary solution. And this is based, as you can see down there, on joint work with Thomas Horowitz, where we have identified a bundle frame implicit programming technique for a different problem class, which on the one hand side might be a bit more complicated, but I would rather say differently structured. So the essence is the same, but the details are different. And this is what you can find in the archive papers on our learning thing. So I'm not sure whether I should go into these details here, but the idea is the following. You start an auxiliary problem as highlighted down there, up there, sorry, in 3.3, which relates to this notion of pulling on stationarity for the specific problem at hand, with an added quantity Q in order to make the problem to identify pulling on stationary points by an optimization procedure well posed. Q is supposed to be a positive definitively quadratic form. Then you can show that this problem admits a solution over H in the tangent space. This is what this curly F is about. So the F is the feasible set for this problem, but this is really the tangent cone. The tangent cone to see admissible at the current iterate U. If the solution of this problem is not zero, then it's a descent direction for the reduced objective curly J. And if you really have some directional derivative, boundedness and linearity of the directional derivative pi prime at U, then you have a uniqueness of U bar there. And the conceptual algorithm which we have at hand now is the following. Given some iterate UK, you solve this problem. Unless you be stationary, you get the descent direction. Then you decide on how far you go into this direction. And then you update the process and repeat the solution procedure until you satisfy H equals 0 solves this problem. Of course, there are many caveats in between, and I will not have time to go into those details. So what we do rather is, it's clear that what I just described is conceptual and idealized because of the non-differentiability. You may end up with a situation where you cannot just continue this process ad infinitum and converge to the solution because of the kinks. In order to circumvent kinks, what we do is now we smooth the directional derivative. This is what this slide is about. I will not go into the details. So whenever you notice a certain complication in terms of, for instance, the step length of the search process getting much smaller than the update direction, for instance, then you would have to go to a different problem which smoothes the directional derivative, so smoothing the sensitivity information. And then I solve the problem which again has the solution. And if epsilon is small enough, even with a descent direction for the original problem, unless you're already at the pulling on stationary point, which is for sure the case if H equals 0 solves this problem. Now, this algorithm which you have at hand now oscillates between 3.3 and 3.4 in terms of whenever we have a complication ahead, which typically is identified by step length of a line search getting much smaller than the update direction. If that's not the case, we just do a classical Amiho type line search procedure. But if that is the case, we rather go to this problem 3.4 with the corresponding choice of epsilon, which may an iterative procedure in its own right, and then compute the descent direction and move forward. And then you can prove that if all is fine and H solves this problem, you get a P stationary point, or in the worst case, a C stationary point. Some numerical results, I think there's not much to say other than it works well. This is a case where everything is monotone, but we even did some investigation of non-monotone mappings F. There's another story to be told that this smoothing, classical zero-order smoothing of a non-smooth N, for instance, may give you a transition from a monotone map to a non-monotone map, which means from a unique solution of the PD to multiple solutions of the PD, which is complicated in its own right and should be avoided. Hence, this first-order smoothing as just outlined a minute ago. But technically, it also works for non-monotone mappings F. So you see the blue curve shows a non-monotonicity by this kink downwards right from the zero. To finish off, let me just go back to the second set, to the original setting of the problem with smooth activation functions, but now the inverse problems context, where the idea is to identify quantitative parameters, which would be here the T1, the longitudinal, and the T2, the transversal relaxation times in a magnetic resonance experiment, and rho is the corresponding proton density. These are three quantitative parameters which would amount to be the U here, and the Y is the magnetization of the underlying set tissue here, which follows typically a Bloch equation, but it's known that the Bloch equations are not fully accurate in certain regimes, but otherwise they're available. So I think I do not go through the details of MRI experiment. Either you know it, and if not, you can read about it online. It's about exciting protons by radio frequency pulses. And then you wait until the excitation state goes back to some rest state. And then you record the corresponding relaxation times in specific dimensions, T1 longitudinal and T2 horizontal, depending on the axis of this experiment, and rho is the corresponding proton density. Mathematically, this gives you again a glimpse how T1, T2, and rho look like in an idealized setting for some phantom image. You see T1 on the left-hand side, T2 on the right, in the middle, and rho on the right-hand side. And the task now is to solve this problem, which means the following: you're measuring in frequency space. So in essence, what this curly F does, it takes a magnetization, Fourier transforms it, and then the P is a subsampling operator because you collect not all Fourier coefficients, but just some of them. So this is what PF of Y does, and the corresponding quantities recorded are this G delta. The delta should remind us that there is noise in the data. Now, alpha U is the regularization term subject to the original ODE, which is then solved voxel-wise with initial conditions and constraints, physically relevant. And again, U contains now the proton density, the relaxation times T1 and T2. So given measurements G delta, the task is to identify the quantitative parameters U, which are unique for every T-sheet type. And the idea is, as I said, the Bloch equations are good, but not perfect, to replace the Bloch equations by measurement data and the corresponding N learned from those data to an artificial neural network training phase. There's a bit more to say, but I don't have the time how this N specifically is trained. But again, we are now completely wiping out the ordinary differential equation and learn from data the solution map from the parameters to the states. And this is what is used voxel-wise for this numerical experiment. Then you can go to the analysis, which I won't do. Everything works out as in the general case. We have an algorithm similar to the SQP method as identified earlier. And I finish off with the results. What you see now here is a comparison between the Bloch equations in the upper row and the learning informed PDE in the lower row. So this is what bottom means here. So you see a comparison in the first column of the T1 maps, in the middle column of the T2 maps, and in the right column of the proton density row. And you can see that the completely data-driven solution map, this is this operator from infinite dimensional to infinite dimensions in a sense, works astonishingly well in these QMRI experiments. So this gives, of course, good hope that we can also go to more complex situations and tasks, time-dependent MRI experiments, and so on and so forth. It's more or less ongoing task in my research group. But this would now conclude more or less the technical part. You see that the difference visualized again between these two columns here. Again, there's an idealized one and there's physics integrated one. Now, what this talk was about, to finish off, I tried to set up a rather generic optimization framework covering optimal control of PDEs, but also specific classes of inverse problems. Where there is a side constraint or governing equation or state equation, a PDE or an ODE which has either components which come from machine learning or are entirely machine learned in terms of the solution operators. We looked a bit into the analysis, but of course more could be said. We looked a bit into numerical algorithms. Remember, we talked about the difference between smooth and non-smooth activation functions. If you go from smooth to non-smooth, this really means an entirely new world, so to speak. And simply smoothing the non-smoothness doesn't do the job, because I told you that sometimes you end up with lack of monotonicity, which then, of course, has some other awkward effects. We talked about a setting where we also learned operators between infinite dimensional spaces, and particularly true for this QMRI example. In a sense, in the first example for the Elon-Kahn equation, we use a hybrid model where we benefit from a non-solution technique, but we implant a neural network-based components. We talked about approximation theory for these operators, and I told you about the non-smoothness. To give a bit of an outlook, what is currently going on in my group, we look, for instance, in the last line at material scientific problems where you have multi-scale nature, where you have a situation where you have a coarse scale solver, which is fine for a coarse scale PDE, and it's available and you can just perform the solution process. But there is, of course, also a fine scale in a two-scale setting, which cannot be solved by classical let's say, finite element type approximation. So now you use a neural network component. You upscale from the fine to the coarse scale by some operator and implant this information into the coarse scale. And this can be done by physics-informed neural networks. And again, this gives rise ultimately to a PDE-constrained optimization problem of a similar nature as shown here, but a bit more complex because of this upscaling procedure. Of course, there is much more to say in terms of also integrating the learning process. Remember, I said up front that the learning is supposed to be done. And then I solved the PDE-constrained optimization problem, but you could integrate these two processes into one common solution scheme where you do not want to oversolve the learning problem ahead of time and solving the control problem. And many more aspects could be said, but I'd rather stop here. Thank you very much for your attention. Thank you.
Great, thank you very much. Are there any questions besides my own? You have to run. Anybody online wants to turn on their camera or type into the chat, and I'd be happy to read it.
I will just leave the full screen mode for simplicity.
Sure.
Okay, so that I can see you somehow.
Oh yeah, I guess you only hear me. Okay.
Yeah, now it's better.
Yeah. So I guess I have some questions. I mean, the first one would be that you have all these universal approximation theorems that you use to justify the scheme, but they're not constructive, correct?
This is correct, yes.
So in essence, you have data from somewhere. You solve that optimization problem on maybe slide 3 or so, the training problem. Yeah. And then you use that, let's say, learned operator in all the control problems. But then there's going to be a significant amount of, let's say, optimization error or uncertainty involved because you probably use some kind of stochastic gradient scheme for that. Do you have any way of quantifying how, let's say, the error in the training from this problem on page 6 influences all the results on pages 7 to 41?
So we do not, a very good question, of course. We do not have such a result at hand right now. So as I said, we just assume this problem here in page 6 down, second half being that it had been solved ahead of time and you have this operator at hand. But I fully agree, we should rather consider this N map as being uncertain depending on the solution process of this problem, but also depending on the quality of the data of that problem. I think, of course, you're an expert. Of course, you can use some aspects of uncertain data and PDE-constrained optimization, but to quantify it further, I think still a lot of work needs to be done. So we haven't looked at this in our group, although we have discussed it in our group that this could be one of our next work packages to try to understand how such errors penetrate through into this component N and how this then influences the solution of the optimal control or the inverse problem. Yeah, so thank you. I mean, there's a similar, so like when you have this estimate on, I think, the next page, there was some soup over, maybe the page after. Like the difference between Qs. There's like a Q. I'll get there.
Yeah.
It's easier.
Hold on.
Here.
There. Go back. Yeah.
Yeah.
So you said let Q and Qn be weakly sequentially operators that satisfy this condition. Yeah. So do you have a way also of then like guaranteeing that your Qn is?
Yeah, this is why we went and do these case studies. For the semi-elliptic PDE, under this assumption that the F is replaced by an N, you can prove that you can use universal approximation, that the Qs and Qns which emerge from that specific setting will satisfy this condition.
I see. Okay.
So that's why here it remained general, but then for the specific examples, it became concrete, where we can also prove, also for the QMRI example, that this condition would hold true in this specific setting.
I see. So that's why I use, I mean, that's the power of using the Nowitzki operators.
Yeah. I mean, here it's general, of course, because here it's more or less without any structure. It just contains the pi map. So however the pi map comes along from the solution with the neural network, as long as it has this property, has this convergence. But in order to satisfy this or to prove this property or guarantee this property, you need to have a specific structure of the underlying problem. So our exercise is to look at, for instance, the semilinear case or the QMRI case, and we could show that in these settings, these conditions can indeed be justified. And of course, in other settings, you may be able to do so as well.
Yeah. Okay. Great. So I see other people are going to meetings now. Other questions from the audience?
Not sure whether there's something in the chat. I will check.
Roland said, thanks for the talk. Need to go. He must have also had a meeting.
Okay. Yeah.
But I guess if nobody else is asking questions, then I can ask another one. So you said
just go ahead. Yeah.
You said you used the bundle free method, or you've developed it further.
Yeah.
Or something similar to it. Do you know if maybe in the examples that you considered that this mapping pi is maybe semi-smooth?
The pi is semi-smooth. This is something we have not looked at. I would need to think a little. I would assume so even.
Yeah, because I remember in the 2016 paper, there's a lemma early on that says if the reduced function is semi-smooth, then there's a much stronger justification for the algorithm. And it was only recently that I think Konstantin Christoph and Gerd Waxman, I believe, proved that the solution operator for the obstacle problem is semi-smooth, which then gives justification to this.
Yeah, I mean, that's a very good question. I think we haven't looked into this detail, but of course, I have written down here general F in this part of the talk, but the specific F comes from a Rayleigh type structure, which is a max after affine transformation. So you have this kind of superpositions of maxes and affine transformations. And of course, for the max operator, we know if you go from LR to LS, R larger than S, then you should be fine.
Yeah.
And since you have a finite penetration depth, because assuming you have finitely many hidden layers, I would assume that you can prove something like semi-smoothness of that operator, and so that you can also. But I cannot say for sure now. But this is a good question. I mean, so what we did, of course, we used our paper, Thomas, and then adopted it to the specific structure. So the idea is, of course, the same. You smooth the sensitivity map, but not the zero-order condition or zero-order constituent. But of course, then you also implant the specific structure of the superposition of these Rayleighs and the affine transformation, which gives you a little bit of a different glimpse at the problem, so to speak, in a different way to compute it in one way or another efficiently.
Okay.
Very nice. But the macroscopic speed is precisely the same as in our paper.
Yeah, very nice.